All right, we have made it to our last section. So one more section on triple integrals. We're going to look at triple integrals in spherical and cylindrical coordinates. And we're going to look at integrals that are set up, maybe in rectangular coordinates, and converting those to cylindrical and spherical coordinates. So for each of these, we'll kind of start off with what these coordinate systems are and how they relate to the ones that we already know, the rectangular system and the polar system. And then we'll talk about how we will convert our triple integrals into these alternate forms. So remember, we recently talked about polar coordinates, and that was another way for us to talk about points in the xy plane. And so this point xy and the point r theta is at the same place in the xy plane. Theta is that angle that we make with the positive x-axis, and r is our distance from 0, 0. So distance from the origin. So keep that in mind when we go into cylindrical coordinates, because basically it's going to be taking the polar coordinates that we have in 2 dimensions and putting a height to it. That's really the only difference. So down here we've got a point in polar coordinates. And this is similar to our point XYZ. And it's again that R is our distance from the origin. Theta is the angle that we make with the positive x-axis. Here, let me grab a different color to highlight theta. And then we get our third coordinate Z, and that is our regular old Z. That's the height that we go to. So let's sum that up over here that we've got, grab a color that's a little easier to read, that R is our distance from, we sometimes say it's from the z-axis, but you could also say that it's the distance from the origin, kind of same thing. That theta is the angle that we've made with our angle from, I think that's what we want to say, angle from that positive x-axis, and this is in the xy plane. And then z is our height. If we want to get fancy about it, we could say that this is the distance that we are from the xy plane. And the relationships that we had with polar coordinates translate over here with cylindrical coordinates. That x squared plus y squared is still equal to r squared, so that's still true. X is equal to r cosine of theta, y is equal to r sine of theta, and z is equal to z. We didn't change anything with z. Z is still how high we go up and down. So hopefully, since we've worked a little bit in polar coordinates, this is not going to feel too terribly difficult or too terribly different is really what I meant to say. This is something that we've done. So when we're looking at triple integrals, what we want to really think about is what happens to that dv, that differential for our volume. So not much is going to be different from this, from when we were doing this in polar coordinates, because that area that we're taking, or that region that we're taking, the bottom of it here, this is a blown up picture of a, quote, we'll put in quotes again, a slice of our region. It's a 3-dimensional slice, so it's got a length and a width and a height. And remember, the bottom here, that's our sort of arced, slice that we have. And that base area, it was our radius that we, so again, that's some point that we take inside of our slice, that radius at that point, and then our delta r times our delta theta. And remember that comes from the arc length. So getting this back arc length, or again, I guess that arc length of wherever we take that point. And then, so that's the area of the base, and then we have our height here, which is our change in z. So that's delta z. So this dv, which, in rectangular coordinates is dx, dy, dz, again, in any order that we want to put that, and that's convenient to us. Here, when we've got our cylindrical coordinates, we're going to have r dr, d theta, and dz. So again, that r comes in right there at the area of our base, just like it did in polar coordinates. So that's really the thing to think about with cylindrical coordinates is they are literally polar coordinates with a height. So that conversion with our integral is exactly the same. We've just now added a height to it. So, we've kind of got down here, we've got our regular triple integral. And then I've got written out sort of what it looks like that usually we integrate with respect to z first, because that often can be in terms of r and theta or one of the other. And then usually secondly, we integrate with respect to r. And sometimes r is given in terms of theta. Sometimes it's just given in terms of r. And then lastly, we have our integral with respect to theta. And those are always going to be angle measures, so those aren't functions. So that's generally why we do those last, because that's going to make sure that's going to, hopefully help us make sure that we don't get any variables out as an answer, because again, these are definite integrals. We should get actual numbers. So some basic shapes that we should know in cylindrical coordinates. So remember, this was a nice way for us to talk about circular regions. This is going to be a nice way for us to talk about cylindrical regions. So in the last section, the regions that we had were, essentially rectangular. I mean, they were like cubes or things that had, straight sides or one of the sides straight that we were taking in our three-dimensional area. Now we have a way to take something that looks more like this, a cylinder, and really make that equation really simple, because this cylinder here if we give it a radius maybe of 2, this cylinder in cylindrical coordinates is literally just the equation r equals 2. It's a kind of a constant function, so it's pretty straightforward, and that gives us that whole region. That would be an infinite cylinder. It's got infinite height both ways, but normally we say we cap the height somewhere at z equals 5 or something, and usually we cap it so that maybe z is not negative, but this is how we talk about a cylinder. We could also have a hollow cylinder, so r could go from 1 to 2. This one here, it would be going from 0 to 2. If we have theta is equal to like pi over 2, this is a vertical half plane. Just remember, in polar coordinates, that was a line, it was a half line. So here, that's going to extend up and down, because now we've got that third dimension of height, so it's going to be a plane. And sometimes we have, things like z equals 4. This is a horizontal plane, and that's normal. That's horizontal plane. That's a horizontal plane in rectangular coordinates as well. That's just a, sort of a sheet that's capping our height at 4. All right, let's take a look at an integral here in cylindrical coordinates. I was right. I almost said the other one. So let's set up our integral, our triple integral, and we're going to find, the hypervolume under e to the z. But we need to figure out again, what are our limits of integration? What order are we going to integrate with respect to? And so we've got this region. So we've got z bounded by 1 plus x squared plus y squared. That is going to be a paraboloid that's going to have sort of the base there at 1. It's going to be an upward bowl looking like this. All right, so there is z is equal to 1 plus x squared plus y squared. We can rewrite that as 1 plus r squared, right, with our cylindrical coordinates. R squared is equal to x squared plus y squared. That's just something that's true from the Pythagorean theorem. And then we're also talking about this circle, x squared plus y squared is equal to 5. That is a circle with radius square root 5. Extend that out there a little bit. Negative square root 5. Extend this one back a little bit. Negative square root 5. And so this is this circle here in the xy plane. Basically what that's doing is saying, okay, it's kind of giving us a left and right bound that we're going to look at underneath that parabola, that parabolic bowl. And z equals 0. So this is the xy plane. And that's saying that we're not going to do anything negative, so it's going to literally be sort of this cylinder right here with kind of that bowl for a top. Okay, that red is kind of making me a little crazy. So let's think about what our restrictions are going to be on our polar coordinates here. So that r, that distance from the origin, r is going to vary from 0 to square root of 5, and z is going to go from 0 to 1 plus r squared. We want to get rid of all of our x's and y's. Z does get to stay when we're in cylindrical coordinates. And theta, because we're going all the way around, we didn't restrict, that we only wanted to look at, say, positive x values or positive y values, that we're going to go all the way around that circle. So theta is going to go from 0 to 2 pi. So our integral, our limits of integration, so I'm going to do theta last, r in the middle. I'm going to do z first because that gets rid of my limit of integration that has variables. We don't need to change the equation at all because there's no x's or y's in it, so it's still e to the z. And our dv in cylindrical coordinates is that r, we'll write it in the order that we're going to do, dz, dr, d theta. So we get r, dz, dr, d theta. And again, remember, it is very important that we write those limits of it, or those differentials, in the correct order, that they are matching up, going from inside out with our limits of integration. It does make a huge difference if you don't have those in the right order. So if you did want to find out what this is, again, the biggest, hurdle that we have to get over in this is getting this set up. Once we get this set up, we have helpers that we can have to help us do this. This first inside integral here, this answer is, we'll do it in orange, you'll get e to the 1 plus r squared minus 1 times r. I suppose that's still in there. So your integral is going to turn into 0 to 2 pi, 0 to square root of 5. And then we'll have inside of here e to the 1 plus r squared minus 1 times r. And you can distribute your r through if you would like. And then our integral here, this one evaluates to be 1/2 e to the 6th minus 1/2 times 5 minus 1/2 times e. You got to do a substitution for that first term because you're going to have r e to the 1 plus r squared. And then plugging in 0 and square root of 5. And so finally, we're going to get the integral from 0 to 2 pi. That 1/2, you can pull that out in front. That's a constant term, minus 5 minus e d theta. And what's nice about this is that these always end up being, all of this stuff is just a constant. And then we get times theta from 0 to 2 pi. So that's going to be pi times e to the 6th minus 5 minus e. And if you wanted a number for this, this is approximately 1,243.2. All right, maybe we'll split these up here. We'll stop this video right here, and then we'll do a second one for spherical coordinates.